The second law of Mendel's is the law of independent assortment, which can be revealed by tracking two different characteristics at once. And so to do this, Mendel basically created what is known as a dihybrid cross. It's the mating of parental varieties that have two different characteristics. So Mendel performed the following dihybrid cross with the following results. He had a P generation with round yellow seeds, wrinkled green seeds. Then F1 generation that had all plants with round yellow seeds. And then an F2 generation that had a combination of traits that were not seen in the parental generation. And so this is how Mendel tested this concept. He had two parental plants here, two parental plants, two parental characteristics, looking at two separate characteristics of each, the shape and the color. And so with a simple monohybrid cross, the hypothesis of dependent assortment, Mendel determined that this was not possible. It didn't give you all of the results that were seen in the F2 generation. So he had to create something more akin to two monohybrid crosses put together, known as a dihybrid cross. And this is his results. So let's look at that in a little more detail. So you have a F1 generation. So when you cross these two individuals, they should be hybrids. And so Mendel found and determined that each allele, each trait had its own probability of being distributed independently. This is an independent assortment. So each trait is independent from each other. So the probability of the seed being round and the probability of it being yellow independently sorted compared to the other trait. So this is why you can have a variety of characteristics found in the egg and sperm. And so when you cross these individuals, so this sperm with this egg, this individual has two dominant alleles for being round and two dominant alleles for being yellow. Compared to this individual here, where the sperm and the egg, when you cross them, it has both alleles for having wrinkled seeds and both alleles for being green. So Mendel needed to explain why the F2 generation offspring had new non-parental combinations and had a new 9:3:3:1 phenotypic ratio. And he suggested that the inheritance of one character has no effect on the inheritance of another character. And so he came up with the dihybrid cross, and he called this the law of independent assortment. So let's apply the law of independent assortment to something that most people are familiar with or have some idea of how it works. When you cross two different dogs, Labrador retrievers are used in this example, black versus chocolate color, and a normal vision versus progressive retinal atrophy, blindness can occur. And so here you're giving the phenotypes. You have four different phenotypes that can be observed. You can have a black coat with a normal vision, a black coat but blind, a chocolate coat with normal vision, and a chocolate coat but blind. Now, things you may not know, you can see the phenotypes because phenotypes are things that you can see. You may not know the genotype. So for these individuals, you may not know the genotype, or you may not know all the alleles that they have, because we know that if they have a black coat, then they must have at least one dominant allele. And if they have normal vision, they must have one dominant allele for normal vision. So this dog here has two dominant alleles for each trait, compared to the black coat blindness, one dominant allele for a black coat, a recessive alleles for blindness. The same is true for the chocolate coat with normal vision, and then chocolate coat being blind, being the only individuals that should have recessive alleles for for both its traits. Now, so these are just reiterating those different phenotypes and stuff. Now, when you cross two heterozygotes, which they have black coat and normal vision, but they carry recessive alleles, you will get the same ratio of offspring. It doesn't mean you will always get these offspring numbers. It just means that you should get this ratio, where you have 9 with normal vision with a black coat, 3 with a black coat being blind, 3 with a chocolate coat being normal vision, and then 1 chocolate coat but blind. So a test cross is the mating between an individual of unknown genotype and a homozygous recessive individual. Because if you do this, then you're now able to show whether the unknown genotype includes a recessive allele. So Mendel used test crosses to verify that he had true breeding genotypes with his pea plants. And so we can do this with a dog with normal eyes, but we don't know the offspring's the genotype for the black coat dog right here. So we know with the recessive dog that has carry 2 recessive traits. So there are 2 possibilities for this black dog. Either their offspring will be all black, because if it contains another dominant allele, then all their offspring will be black. But if it contains a recessive allele, then you can either get 1 black or 1 chocolate, or half black, half chocolate. So this should be the possibilities of when you cross these 2 individuals. And if you do get a chocolate colored puppy when you cross these 2, then you know that this individual here has the recessive allele. And this may not seem something that, most normal people would care about, but if you are a professional dog breeder, this is something that you will do, and you actually search for and you look for individuals who have the alleles that you want to breed. So Mendel, using his strong background in mathematics, he knew that the rules of mathematical probability affected the segregation of alleles during the formation of gametes and the reforming of pairs at fertilization, because that's all random. So the probability scale ranges from 0 to 1, with 0 being around 0%, 1 being 100%. These are the numbers they use in probability. So a probability of 1 is certain, where a probability near 0 is not certain. So the probability of a specific event is the number of ways that event can occur out of the total possible outcomes. Determine the probability of 2 independent events uses the rule of multiplication, in which the probability is the product of the probabilities for that event. The probability that an event can occur in 2 or more alternative ways is the sum of the separate probabilities, called the rule of addition. So let's make that make sense to you guys. It's a bunch of words, but pictures, of course, can tell a different story. So if you are an F1 generation, so a hybrid, a male or a female, then the probability of your gametes either being a dominant or recessive allele is equally 1/2. So it's like a flip of a coin. This female has 0.5% or half a chance of passing along her dominant allele and 1/2 chance passing along the recessive allele. And so when you cross these 2 individuals, so getting this dominant allele and this dominant allele is both a 50-50 chance. However, the probability of being a homozygous dominant for this allele, you have to multiply the 2. So this is the rule of multiplication. And so there is a 1/4 of a chance that this individual here will have the dominant alleles. While on the other side of that, there is a 1/4 of a chance, or 25% of a chance, of the offspring developing, having 2 recessive alleles. So because of that probability and our knowledge and information of how traits are passed on, then some traits in humans can be tracked through pedigrees. So in a simple dominant recessive inheritance of a dominant allele and a recessive allele, The recessive phenotype always results from a homozygous recessive genotype. However, the dominant phenotype can either be homozygous dominant with both dominant alleles or heterozygous with one dominant, one recessive allele. Now, in nature, though, wild type traits or may be what's observed. It's not necessarily specified by a dominant allele. So sometimes the prevailing trait could be the recessive genotype. So sometimes in nature, the dominant traits or the dominant alleles may not be what's actually the most common trait in the population. So for example, freckles and no freckles. Freckles is actually the dominant trait, but it is less common than individuals with no freckles. While some things are rare, for example, having albinism, which means you have no pigment, is less common and it is recessive. Another example of that would be free earlobes and attached earlobes. Where free earlobes are more dominant and more common in the human population. Inheritance of human traits follows Mendel's law. Mendel's laws have shown that they are common, universal. And so one way to track human traits is through something called a pedigree. It shows the inheritance of a trait in a family through multiple generations. It can demonstrate if something is dominant or recessive, and it can also be used to deduce genotypes of family members who may not have shown a phenotype to determine the trait, and the potential for future offspring to determine what your future offspring may. So here is a simple pedigree showing you 2 generations of grandparents. So these are one set of grandparents, another set, and this is the male and female, the man and woman who got married and had offspring. And you can see that these 2 individuals are heterozygotes, where both have parents that carry the recessive alleles. And so they have children, and then so their children are showing 2 different phenotypes. One is showing the attached earlobe, which we know to be recessive, fully recessive, and then one has the detached earlobe, which we know they must have one dominant allele. So we don't know for sure if she is homozygous dominant or heterozygous until she has offspring of her own. Another example of that could be seen in straight hairlines versus widow peaks. And so this is another pedigree done in a little bit of a different way, where it shows the grandparent generation or the first generation, their offspring, and then the mating of Henry and Isabel here, producing a 3rd generation, where Kristen here has a straight hairline and Libby has a widow's peak. Now, from these traits, we can determine the individual genotypes of the past generations and Kristen and Libby. And so we can tell here that since Kristen has a straight hairline, that because her parents do not have straight hairlines, that it must be a homozygous recessive trait, which means they must carry a dominant allele, and which means Libby is inherited one of the dominant alleles from her parents.